Okay, it is now my pleasure to introduce Carnegie Mellon's Provost and Chief Academic Officer, Jim Garrett, to introduce our keynote speaker. A nationally recognized engineer and a lifelong Tartan, Provost Garrett has been a steadfast supporter of the Scott Institute. So please join me in welcoming Provost Garrett.
It often happens when the provost is asked to speak that half the room leaves the... So, thank you, Daniel, for that very kind introduction, and thank you for serving as the executive director of the Scott Institute for Energy Innovation. We really benefit from your leadership. I also want to thank all the previous speakers on the panel, plus all the other speakers that will speak today and for the rest of the week. They share their insights, their expertise and enthusiasm with us, and we really benefit from it. So let's give all of these previous speakers and everybody who's speaking here at Energy Week, let's give them a big round of applause to thank them. And I really am very glad to be joined by members of our CMU leadership team, past and present. I see a number of folks here, including Dean Ramaya Krishnan, who you just heard from. On behalf of President Farnam Jahanian, it is my true pleasure to welcome all of you here to CMU. And for those of you who've been here before, welcome back. This is an afternoon in which we're going to discuss very important topics, related to this Energy Week. So this week represents our commitment to exploring the most pressing challenges and innovative solutions in energy, a mission that is at the heart of CMU's interdisciplinary approach to global problem solving. As technological innovation accelerates, Carnegie Mellon is not just witnessing change, we're actively participating in shaping it. And today's conversations explore how artificial intelligence is reimagining skills, productivity, and strategic approaches within the energy sector. It is certainly a timely topic and one that we are very much delighted to facilitate. So at this time, it's my pleasure to introduce our keynote speaker, a leader who embodies the very essence of strategic energy innovation. Dr. Marianne Walck is the director of the National Energy Technology Laboratory, where she manages an extraordinary complex of over 1,300 employees and guides more than 1,000 research and development projects across 50 states. Her career is a testament to cutting-edge energy research and leadership. It's spanned 13 years at Sandia National Laboratories, where, among other leadership roles, she served as the vice president for the California Laboratory and its Energy and Climate Program. With a master's and doctorate in geophysics from the California Institute of Technology and a bachelor's in geology and physics from Hope College, Dr. Walck brings deep scientific expertise to her role in the field. She leads NETL's critical work supporting key U.S. Department of Energy offices, fostering important relationships with utilities, academic institutions, governments, and carbon management stakeholders. We are truly delighted to have her join us here, to hear more about her influence and impact. Please join me in welcoming Dr. Marianne Walck to the stage. Thank you.
Well, good afternoon. When you said everybody left for the provost, I was thinking probably everybody left because the national lab person is going to come and talk next. But here we are. So I've been here all day. I've listened to the fascinating talks and panels that we have had this morning and this afternoon. And this one's going to be a little bit different. I'm not talking about energy for AI, I'm talking about AI for energy in this particular case. So we're going to be talking about from perspective from the Department of Energy and the National Laboratory System within the Department of Energy. So I'll talk a little bit about that. I'll talk a little bit about my lab, National Energy Technology Lab, which has an office here in Allegheny County in Pittsburgh. And I will talk a little bit about some of the things that we are doing at a very high level some of the things that we're doing at NETL that use AI to try to help solve some of our energy technology challenges. So that's what I hope to do. Let's see if these slides work. Whoops, that's the wrong way. Okay, I always do that at least once in a talk. So hopefully that's it for today. We'll see. So that's my title, AI and Energy at NETL. So let's start talking about what the Department of Energy priorities are for artificial intelligence. And of course, we have a new executive order on artificial intelligence that has come out since January 20th. And I know that the current administration views artificial intelligence as a very important part of American energy technology innovation and innovation in general. And then we have a new Secretary of Energy also, Chris Wright, who comes from the natural gas industry. And he has been very focused on advancing energy addition, not subtraction. He's got a focus on innovation. He's a very strong supporter of the national laboratory system, and he also, of course, wants to strengthen grid reliability and security. And I think you can see that all of those things require artificial intelligence in these days to make progress on those things. So very much coming down from the top here. Next, let's talk a little bit about our national laboratory system. So not all of you may know that the Department of Energy sponsors 17 different national laboratories. They're across the country, and we have, they range from science to applied energy to environmental management to national security. So you can see this in this sort of rainbow chart. My national lab here is in the orange, down there at the bottom right. We're one of the 3 applied energy laboratories in the system. So there's one that's focused on renewable energy technologies, NREL, which is out in Colorado. Idaho National Laboratory, where I actually worked for 5 years right before coming to NETL, is focused on nuclear energy. And then NETL is sponsored by the Office of Fossil Energy and Carbon Management and has traditionally focused on fossil energy technologies, and now more recently has had a real focus on carbon management as well as fossil energy, and of course on sustainable development of fossil energy continues to be a focus for NETL. So we have a wide variety of expertise across the national laboratory system, ranging from the very fundamental, for example, Fermilab, they look at muons traveling through the Earth's crust and whatnot, looking at the origin of the universe. And then we have places like NETL where we're more focused on how we get energy out of the ground and into our ecosystem for us to consume. So, and then of course the whole national security laboratories are focused on the nuclear deterrent as a big portion of their mission. So a wide variety of things, many, many thousands of scientists and engineers across the national lab system. So a little bit more about the laboratory that I work in, National Energy Technology Lab. It's one of 3 applied energy labs, as I mentioned. It's the only Department of Energy owned and operated lab. So we call it a GO-GO, government owned, government operated. The other 16 labs are GO-COs, government owned, contractor operated. If you have an afternoon, I could explain to you why that is. Why are we the only GO-GO? Why are the other ones all GO-COs? But we don't have time right now, so if you have an interest, let me know and I can talk about it. But NETL has 3 different locations, and 2 of them anyway have a deep, long history with the Bureau of Mines, which was actually dissolved back in 1996. But the Pittsburgh site goes back to 1910, and there's actually a coal mine on site from, it's actually a mine safety mine. It never produced coal commercially. But there is a long history of the coal, region that we live in at my laboratory. So we have a laboratory in Pittsburgh. We also have one in Morgantown, West Virginia, which started back in the 40s. And then we have one out in Albany, Oregon. Another interesting thing, why do we have a site in Albany, Oregon? Well, they focus on metallurgy out there, and they've also been there since the early 1900s, and it was also a Bureau of Mine site. And we have a little energy technology office in Houston as well that helps us keep connected with the oil and gas industry. So we are part of DOE's Office of Fossil Energy and Carbon Management, and we do 2 things. We do research and development at our laboratory, And all 17 national laboratories do research and development within their laboratories. At NETL, because we are government-owned, government-operated, we also deploy programs for the Department of Energy. So we run competitions for funding, and we award funding, and then we manage the projects. And so this is one of the aspects that a go-go can do that a go-co cannot. But today, I'm going to be focusing on NETL's internal research and development aspect. Right now, we actually have a workforce of more than 1,900. We have about 700 federal employees and about 1,300 contractor employees at our laboratory. So, what do we do at the laboratory? We are actually pretty focused on 6 different areas. And one of them is related to that program deployment I just talked about. So that's the program execution and integration competency that you see at the bottom right. But we also do 5 other things pretty well at our lab. Some of the bigger laboratories and some of the national laboratories get up to 15,000 or more people. So we're one of the more small ones. Some of them do everything that you can possibly think of. NETL is a little bit more focused. So we have work in geological and environmental systems, as you might imagine, since we have a long history in fossil energy, but also carbon sequestration, subsurface hydrogen, all sorts of interesting things below the surface of the Earth. We do materials. I think probably all the national laboratories do materials. It's important to a lot of different things that you would do in energy. We also do energy conversion engineering, so how do we take thermal energy and convert it into other things and make chemicals and things like that. And then strategic systems analysis and engineering, more life cycle analysis, techno-economic modeling of different energy systems, and also, of course, computational science and engineering, which is really important for some of the things we do in AI. So those are the various things that we do at NETL specifically. And then we apply them to various problems. So on the left-hand side of the slide, you'll see some of the applications that we actually are looking at to use artificial intelligence and machine learning. So these are some of the things we're interested in looking at the laboratory. So certainly oil and gas production would be one, carbon storage another, sensors and controls for a variety of different things that we need to do, advanced turbines, solid oxide fuel cells, rare earth elements. Critical minerals is a big deal right now. We were talking about some of the things that might be bipartisan in the new administration. Critical minerals is one of them. Everybody knows it's important for us to be able to access these materials, and our laboratory is working within DOE on that. And we can use artificial intelligence to help us make progress on that as well. So, advanced coal processing, a lot of different things. So what I'll be doing throughout this talk is to talk a little bit about some samples in different areas where we are applying artificial intelligence and machine learning towards solving some problems in these areas. And of course, we've built up a little bit of infrastructure at the lab to attack that. We have an institute which brings people from all 3 of our sites and some external people together, which we call SAMI, the Science-Based Artificial Intelligence and Machine Learning Institute. And it's a collaborative, and I'll talk about that for a minute in a second. And then we also have a couple of hardware facilities that I'll just mention very quickly. So our Science-Based Artificial Intelligence Machine Learning Institute, there's a website for it you can look up on the web. It supports our life cycle of data, of course, and it's got secure private collaborative workspaces, and it's used as a collaboration tool for people across the laboratory to get together, focusing on these science-based AI and ML modeling coupled with the data that we have. And we have a lot of data at NETL, and I'll talk about that in a minute as well, to help provide some of these advanced energy models that we do. And also we're interested in standards and platforms as well. So SAMI is a really nice construct for our staff to be able to work and collaborate together and collaborate with people in the external world as well. We have a couple of hardware facilities. One we're building, sort of a bump out of one of our buildings in Pittsburgh that is housing our artificial intelligence focused machine, which we call WATT. And also has collaboration spaces and will be the data center for our Pittsburgh facility, and we're working right on that right now, and it's almost done. So these will serve us well in the future. And then down in Morgantown, we are building a brand new building from Greenfield for a computational science and engineering center to house our more traditional HPC machine, which we call Joule, and is expected to be just started actually last fall, and we expect it to be finished in 2027, and so that'll be a data center for our Morgantown site. So we do have some good facilities available for using these kinds of algorithms and techniques to be able to have impact on our energy programs. So let's talk a little bit about some of the other things that we do. One interesting, I particularly find this to be interesting, thing that we do is this data platform called EDX. And so this is coordinated and curated set of data for all fossil energy and carbon management programs. A lot of it's subsurface data, but not all of it. It's in a variety of different formats. It's all put together. We've just moved it to the cloud this year, and it is a lot of it's publicly available or data that our researchers can use to focus on these problems. And it is a really unusual collection of data that it would be very difficult to assemble otherwise. And so we've used our government funds to put this all together in one place where everybody can get at it. I couldn't get at it personally. I mean, I'm not smart enough to do that. But our data scientists can go in there and grab the right kind of data and use it with these tools to create models and create solutions. Another area that we've worked on hard is integrated energy systems. We've done this with the other two applied energy national laboratories. And here we're thinking about these distributed systems where we might have a variety of different types of energy sources that are co-located, which could be used for either electricity or potentially high heat sources to make chemicals, desalinate water, create hydrogen, those types of things. How do you optimize those and put them together and create a system that actually works in a grid environment? And IDACE is a center that, and some pieces of software that we've put together. It actually won an R&D 100 award back in 2020 to do this type of optimizations for the future energy systems that we're going to need in this country. So those are a couple of examples of things we're doing. Let's talk about a few more. We have a group we call Gaia, which is a geospatial data analysis group. They use the EDX platform. I'm sure everybody at universities must use just as many acronyms as we use in the DOE world, right? Maybe not, but we're rich, we're acronym rich in the DOE space. So everything pretty much that I'm going to talk about today has acronyms. But here's an example of a few things that this geospatial data team has used the EDX database to put together. So let's talk about MapIt for a second. This is a collection of data and tools that you can use to help create a permit to drill a Class 6 injection well. What is a Class 6 injection well? Anybody know? You do. Good. It's a kind of well you have to get a permit to in order to inject carbon dioxide into the subsurface to sequester it. It's a particular type of well. It's really difficult to permit, and it takes a long time. So they put together a tool to help people be able to apply for these injection well permits. CO2 Locate is a collection of subsurface data from across the country that can be used to analyze whether a particular location might be a good place to put carbon dioxide in the subsurface. There's a variety of different types of geological criteria that you would need to have in order to be able to successfully put CO2 in the subsurface and have it stay there. And you want to be able to screen, how can we do this? Is this a good spot? Is it close to my CO2 source? Do I have a pipeline that I can get it there? All those types of things they've developed this tool, CO2 Locate, in order to try to help that situation. And they've used machine learning and artificial intelligence and all the data we've got in EDX to be able to do that. We've also been developing models to look at energy infrastructure, such as offshore pipelines. That's what the AIM, Advanced Infrastructure Integrity Model, looks at as well. So there's some examples of some of our geospatial team has been developing for energy applications. Another thing we're doing is we're actually working with a commercial company called Cerebras, which has developed an architecture for artificial intelligence machines, which they call the wafer scale engine. And what NETL has done is written an application programming interface, which they call WFA, Field Equation Application Programming Interface, which is aimed at making this wafer scale engine more usable and optimizing it to solve regular PDE-based supercomputing programs like, computational fluid dynamics or other types of more standard scientific modeling programs. So they've made a great, really fun things, been able to speed this process up quite a bit using this wafer scale engine, which is a really huge chip. It uses low energy and it's large by itself, but the computational architecture actually saves a lot of space compared to conventional GPUs. But it was all designed for AI architectures, and what we did was help make it more useful for sort of normal supercomputing. So that's another interesting aspect of what we've been doing at NETL as well. And we're very proud of this collaboration with industry. Another tool that we've been using, going back to the subsurface, and I always go back to the subsurface because, as they mentioned in the introduction, I'm a geophysicist, and so I like the subsurface. And when they were talking about, in the last panel, about how you never know, you might not actually do what you were trained to do. So my PhD thesis was looking at velocity discontinuities in the upper mantle of the Earth, 670 kilometers down. So obviously I don't do that anymore, right? So I think if we all thought about talk to each other, those of us who are farther along in our careers, and think back about what did we do when we finished school and what are we doing now, I think we could verify the fact that sometimes things change, and that's okay. You use your academic training for a variety of different things, and it all works out really well in the end. But that said, anytime we go back to the subsurface, that's what really makes me excited. So I've got lots of subsurface examples for you today. And this one is related to critical minerals. And so it's a tool called URC, the Unconventional Rare Earth and Critical Mineral Resource Assessment Method, or tool. And what this has done is looks at the different geological parameters around identified rare earth element deposits, uses AI and ML to figure out, okay, where should I look? Because there's dirt everywhere, there's rocks everywhere. Where are we going to find those critical minerals? How do I know where to look? And this particular tool took a lot of the data out of EDX, applied all those geologic criteria to it, and made recommendations in terms of where we might find some really good critical mineral deposits. And it was actually very successful in an initial study where they identified the largest unconventional deposit of magnetic rare earth elements to date, which was in the US at the Brook Mine property near Sheridan, Wyoming. So unconventional there being in that particular case, associated with some coal deposits, which would not necessarily be where you would look for these rare earth elements to begin with, but they were there, and this tool helped them find that. So this was all due to the machine learning, and we never would have been able to sift through all that data without that application. In another aspect, we also do a lot of solid oxide fuel cells at NETL. And we're looking at electrode degradation. We're using machine learning and actually the wafer scale engine technology. On this also, we've got a lot of applications at NETL where we do hardware in the loop, so we can do machine learning simulations and then try it out on the hardware, get feedback, go back and continue along with the process and really improve the technology. So this is another example, and in this one, we're partnering with Carnegie Mellon, and so wanted to make sure to bring that aspect out as well. And the idea, of course, is eventually we'll be able to produce electricity more cheaply using hydrogen. Another example is in high-performance polymers for gas separation, and this one is maybe a little bit more traditional to thinking about what you use machine learning for in terms of material screening, right? This is a sort of a classic thing in the R&D world is, how do I design a material? Well, using machine learning is great for that because you can rapidly try out a whole bunch of different aspects. If you know enough about the material and you can, you've got your data, you can screen well. And so in this case, we screened a whole bunch of different polymers for permeability and selectivity, and we were able to predict which really narrow down from a very wide initial spectrum, which polymers would have the best performance for separating out carbon dioxide from methane, for example. So that's another thing that we're doing. We're also into the autonomous discovery world as well. I toured Carnegie Mellon's autonomous lab a couple of weeks ago. It's really amazing. I wouldn't say that NETL is quite that far, but we are dipping our toes into the autonomous discovery world where we're looking at 3D printing, robotics, combining with machine learning to provide feedback to, and in this particular project, we're looking at how we can optimize cooling designs for gas turbines using that type of methodology. And this is an internal research project we're doing at NETL using our computational resources, our 3D printing, and our robotics capability as well. And I believe this is my last example. So go back to the subsurface. So in this particular case, we're looking at subsurface trend analysis workflow enhanced with image segmentation. So a lot of subsurface data that you're going to find out in the world might be in the form of a map. And this is the result of people doing a lot of mapping and putting data into map form, and it might even be on a piece of paper somewhere in a journal from years ago, but you don't want to go back and have to try to redo this study, right? So what can you do? If you can scan the map and you can use this kind of image embedding tool, which we found extracts and accurately labels these images with a very high level of precision. We've done this in a 2D environment and applied to some oil and gas data in the Gulf that's south of Florida and Mississippi. I'm not going to get political on this. So we are, and we use our data from our energy data exchange, and right now our people at NETL who have done this analysis are extending this tool from 2D to 3D because there's a lot of 3D subsurface data out there in the form of well logs and other, other types of images that we can then take from the analog to the digital and then develop these trends using the wonderful tools that we have available to us today. So for those of us who have been around a long time and have been dealing with subsurface data and thinking about how can we use this, the tools that artificial intelligence and deep machine learning provide to us are really magnificent leaps forward in our being able to understand what's happening in the subsurface, which I find to be really fascinating. So with that, I'll just mention that NETL, the lab, has a variety of ways we can partner. We do work with many universities in the region. We want to do more. We have cooperative research and development agreements available. We've signed MOUs. We would love to have students come and work at our lab and do cooperative work at the universities. And we're very interested in, if you're interested in taking your AI and ML techniques and having them applied to a real world problem, we've got lots of real world problems that we can apply them to. I talked about a few of them here for the last few minutes. And I hope that that piques the interest of a few of you in terms of working with our laboratory. So thank you very much for your attention. Appreciate it.
Thank you, Dr. Walck, for that great keynote. We have time for just a few questions before we cut to a break. So are there any students in the room who have a question?
That's the problem with going right before a break, right? Yeah.
Yeah.
Thank you very much. The conversation or the phrase critical minerals has become even a little bit more mainstream lately. Hard to believe. But the need for critical minerals when it comes to batteries and energy in the United States, and the connection that that has to national security, because battery production currently does not exist to what we need in the United States. It's made in China. The possibility of backdoors and so forth. Can you just talk a little bit about the importance of critical minerals and the continued development of them in the United States when it comes to batteries and storage and the whole conversation that we're having around energy today? Thank you.
Yeah, sure. I can talk about that a little bit. I think many people know that there's a variety of materials and naturally occurring materials or minerals that we need for a lot of things. We need them for batteries. We also need them for our national defense as well. And the fact of the matter is there's only one mine in the US that's currently operating. It's in California that produces rare earth minerals. And there's critical minerals and there's rare earths. Rare earths is a subset of critical minerals. They're not rare, but they occur in very low concentrations in ores. So if you want to dig up some ground and grab something out of it, that if it's in a very low concentration, you have to do a lot of processing to it. That makes it very expensive. It can also be environmentally damaging because you might need to use harsh chemicals or other types of separations to pull those minerals out of the ore. So the fact is that we don't actually do hardly any processing of rare earths or critical minerals in the United States. Most of it's done in China. So this is it's a national security issue for a variety of reasons, both because of its direct connection to the fact that we use some of these materials in our national defense, but also because we use them for everything we do every day. And these all come from overseas, and so we're very dependent upon foreign entities for the supply of these materials. So there is a big push within, and there has been for the last few years, it's really started to do more within the government to help the supply and the processing of how we get the critical minerals out of the ore once we have them, and increase the reliability and security of the supply chain for critical minerals in the nation. And the Department of Energy and National Laboratories are certainly very involved in that, and NETL is in a leadership role there with regards to that. Fossil energy is one of the areas. There are several areas within DOE and the government where there is funding for critical minerals, but fossil energy carbon management is one of the prime places. And we've started several projects related to that. We've also done previously, even before this push, there's a big push for this in the bipartisan infrastructure law that was passed a few years ago, so quite a bit of funding provided for that, for critical minerals R&D. But even before that, NETL was working on finding these critical minerals in unconventional places, like produced water from oil and gas wells, or acid mine drainage, or coal ash deposits that you find all around Appalachia from old coal mines. They can have some concentrated critical minerals within them. And then, of course, there's always things like lithium as well, which is very important for lithium-ion batteries, and a variety of things, and we're finding those in various waters around the nation as well. So it's a little scattered, but I'll stop there. If anybody has any additional questions about them, I'd be happy to try to answer.
We have time for just one final question.
Thank you. Our first speaker of the day mentioned or talked about geothermal energy a lot more than I was kind of expecting, and I thought it was very interesting. She also mentioned, I believe, that some of the drilling techniques that are used by oil and gas are being used to unlock geothermal potential in areas that otherwise were not available even a few years ago. Wondered if your laboratory has anything to do with helping folks to cite potential geothermal sites that, again, otherwise would not have been available a few years ago.
Yeah, thanks for asking that. So one of the things she talked about was enhanced geothermal systems. And so basically, what's going on there, the previous thinking was that when you need to get really hot water or steam to create geothermal power, so you would have to be near a volcano most of the time in order to get a geothermal gradient below the surface that would give you that much heat. But with enhanced geothermal, the idea is that you can have a well that you then basically frack it, and that's where the oil and gas technology comes from. Create pathways, circulate water through hot rock, and then pull it up the other side and use that. And so that creates a lot more of the subsurface than is available to us than just very small areas near volcanic areas. So that's the basics of geothermal. I think there's enhanced geothermal. There's also drilling technology that's important, of course, because the types of rocks that you drill for geothermal are fundamentally different usually. Not so much necessarily for enhanced geothermal, but for traditional geothermal, you would be drilling in volcanic rocks or plutonic rocks near volcanoes that are typically much more difficult to drill through, just to be honest. So much time you would find oil and gas in sedimentary rocks, which are easier to drill through. So there's been a lot of back and forth between the oil and gas industry and the geothermal industry on drill bits and how to drill successfully to make these completions. So yes, we are basically, enhanced geothermal is applying fracking to geothermal systems so that we can create hot water, which we can then use to make to steam and drive a turbine and create electricity.
Well, Dr. Walck, thank you so much for your leadership of the National Energy Technology Laboratory. Thank you for your partnership with Carnegie Mellon, and thank you so much for being at CMU Energy Week and sharing your wisdom with all of us.
Thank you. Thanks.